Welcome to Maths with EJD. In this video, we continue with constrained optimization problems. Constrained optimization, say methods, right? So we had considered Lagrangian multipliers, which seems to be the most popular of them, Lagrangian multipliers. So now we will be looking at sequential quadratic programming, sequential quadratic programming. And in the next video, we'll be looking at interior point methods. Interior point methods. Okay, so just like I said, Lagrangian multipliers done. Now sequential quadratic programming. Let's go for that. Sequential quadratic programming. SQP for short. Okay, so sequential quadratic programming or SQP is an iterative method for solving nonlinear optimization problems. For solving nonlinear optimization problems, it is used for constrained optimization, where the objective function is nonlinear and the constraints can be equality or inequality constraints. Okay, sequential quadratic programming approximates the original problem by solving a sequence that you see where the sequential is coming from by solving a sequence of quadratic subproblems, Hence, the name sequential quadratic. Sequential quadratic. Okay. All right, let's look at the general problem formulation. General problem formulation. So the general constrained optimization problem is minimize f of x subject to gi of x, which is an equality constraint, where I is from 1 to m. These are equality constraints, as you can see, equality constraints. And then you have hj of x is less than or equal to 0, where all the j's are from 1 all through to p. And these are the inequality constraints. So as like I said, this is equality constraints, and this would be inequality constraints. Okay, so that's the general formulation. But of course, what do the terms mean where f of x is the objective function, gi of x are equality constraints. Then hj of x are inequality constraints, like I showed up there, inequality constraints. Okay, now let's look at the SQP approach, the sequential quadratic programming approach. What does it look like? So at each iteration, sequential quadratic programming solves a quadratic approximation, solves a quadratic approximation of the Lagrangian function. Thankfully, we've seen Lagrangian function in the previous video of the Lagrangian function and updates the solution All right, so let's look at the first step in that. We have the quadratic approximation of the Lagrangian. Okay, so the Lagrangian problem, the Lagrangian rather, for the problem is L of x lambda u is equal to f of x, that's the objective function, plus summation from I equals 1 to m of lambda I of the gi of x, talking about the equality constraints, plus summation from j equals 1 to p. Then we now have mu j multiplied by the hj's of x, talking about the inequality constraints. Okay, so the SQP method, the sequential quadratic programming method, approximates this Lagrangian by using the following second order Taylor expansion. So that is the Lagrangian of x plus delta x plus lambda mu. So we have a bit of extension of the x, right? And that is approximately the Lagrangian of x lambda mu plus the nabla of f of x transpose multiplied by delta x plus half delta x transpose h sub x delta x, like that. H sub x delta x. So L of x plus delta x, comma lambda, comma mu is approximately lambda of the Lagrangian. I mean, I'm talking about the Lagrangian of x plus delta x, comma lambda, comma mu is approximately the Lagrangian of x, comma lambda, comma mu plus the gradient of f of x transpose dx, delta x, right? Plus half delta x transpose h sub x dx, like that. Okay, so the next step after this, which is the second step after the quadratic approximation of the Lagrangian, the next step is linearization, linearization of the constraints, linearization of the constraints. Okay, so the constraints gi of x equals 0 and hj of x less than or equal to 0 are also linearized. They are also linearized around the current iterate x, around the current iterate x. So we have gi of x plus delta x, approximately gi of x plus the derivative, the grad of gi of x transpose delta x. Okay, and then we also have hj of x plus delta x is approximately hj of x plus nabla, that's the gradient of hj of x transpose delta x, like that. So after doing that step, we go to the third step, which talks about solving the quadratic, solving the quadratic sub problem. Okay. So at each iteration k, the following quadratic subproblem is solved. The following subproblem is solved. That is minimum delta x for nabla f of xk transpose delta x plus half delta x transpose hk delta x. Okay. And then that is subject to gi of xk plus nabla gi of xk transpose delta x equals 0 for every I, for all I, and then we have hj of xk plus nabla of h sub j of xk transpose delta x is less than or equal to 0, okay, for all j, just like this is for all I. So we have that as so we solve the quadratic subproblem at that level. So having done that, we update the step, the next step after that, that's step 4 now. So update step. That may sound like like a lot, but an example is going to drive the point home. So after solving the quadratic subproblem, after solving the quadratic subproblem, so it's more like a Lagrangian multiplier, at a very high level. After solving the quadratic subproblem, okay, the update, for x is computed, as xk plus 1 equals xk plus delta xk, like this. So this is the update rule. So now we want to check for, let's go for some, okay, let me switch it over. Let me do this and then this. So let's do some example. First, okay, I mean, just one example is enough because the process is tedious already. So consider the following. It's for solving nonlinear constraint problem, right? So consider the following nonlinear constrained optimization problem. That is minimize, get the minimum value of x, minimize f of x equals xi x1 squared plus x2 squared, two variables, and then g of x, the equality constraint is xi x1 plus x2 minus 1 equals 0, and then h of x equals xi minus 1, which is less than 0. This should be x1, not xi. x1 minus 1 is less than or equal to 0. Okay, so that's the problem we need to take care of. And then we go for step 1. We need an initial guess. So step 1, initial guess. Okay. So let the initial guess be x naught, which is equal to 0 0.5, 0 0.5. It's a guess, so you can pick any value of your choice. Then we go for step 2, where we talk about the Lagrangian and constraints. The Lagrangian and constraints. So we say the Lagrangian is Lagrangian of x lambda mu equals x1 squared plus x2 squared plus lambda into x1 plus x2 minus 1, all right, plus mu into x1 minus 1. Okay, put all of that together. So we know that the grad of f of x is equal to, that means we differentiate with respect to the function, this function itself now. So that would just be that's partial f partial x1, comma partial f partial x2. Okay, just for this part now, because that's the f of x. All right, so that means we simply have 2x1, comma 2x2, and that settles that. And then we have the grad of g of x. So we are differentiating g of x, which is basically this, into, so with respect to x1, so that's partial g, partial x1, partial g, partial x2, and that is equal to 1, comma 1, and that goes. Then lastly, we also have the grad of h of x, so that's partial h, partial x1, comma, partial h, partial x2. So that means this other one now. So differentiate, of course, that is x1 minus 1. So differentiate x1 with respect to 1, we have 1. H with respect to x1, we have 1. There's no x2 there, so automatically that will be 0. Okay, so we get those two. And with that in place, we go for step 3, which is where we have this quadratic subproblem. So quadratic subproblem now is going to be, so we have half of delta x1, delta x2 into 2002, okay, 2002. That's talking about this 2x1, 2x2 now. So 2002, and that is multiplied by delta x1, delta x2. Okay. Okay, let me even see how we got here. Okay, that's the transpose of the gradient evaluated at those 2 points. So, I mean, if this is not so clear, so imagine this as, this is delta partial. So it's the original function, right? Partial f, partial f, partial x1, this one here. And this is, and this one here is partial f, partial x2. So I'm trying to see. Yeah, I think that's how that goes. Um, okay, let me try to make something like this. Imagine you have x1, x2, and then you have x1, x2. Okay. Yeah, so this is like the next level. What's that expression again? I think That's where we should look at that. So where we are talking about sub-problem, right? So this is grad of f of xk transpose multiplied by delta x. Okay, so that's like f of x1, and then we have f of x2 also. So in short, so following from this 2x1, 2x2, so uh so differentiate, so 2x1 with respect to 2x1, we have 2, then 2x1 with respect to x2 is 0. Then we go to 2x2. Differentiate 2x2 with respect to x1, that is 0. Differentiate 2x2 with respect to x2, that is 2 again. And that is why we have this center one. Okay. So with that in place now, we can continue that expression. So we have delta x1, delta x2. This plus 1, 1, 1, 1. Well, the transpose of that is easy to write, so there's no point trying to make it unnecessarily difficult. Okay, let me even wipe out this whole thing. Let me rewrite it because I need some space there. I need a whole lot of space. Okay, that's not necessary. Let me bring it back. Let me bring it back. These are constraints now. The other things are constraints. Yeah. So, yeah. So we have this now. This plus this plus 1, 1 into delta x1, delta x2, like this. Then, this would now be, so when we talk about the quadratic sub problem, if you remember what we had up here, so we have it, we still have it like a standard problem. So we want to minimize subject to this, right? So this quadratic sub problem is us minimizing this subject to, subject to, so 1, 1, delta x1, delta x2 equals 0. And then we have the other one that is 1, 0, delta x1, delta x2. So that's the 1, 1 is coming from, okay, this is not, okay, this is less than or equal to 0, being the inequality constraint. That is coming from, delta gx 1, 1, then the other one is 1, 0. Okay, so we have this now. So with that, we move on to this next step, which is step 4. So step 4 is where we solve the sub problem. Okay. So we say after, now I'm not going to bother so much about it because we are going to finish it up with Python code because the whole thing is looking tedious already. Okay. So after solving the quadratic sub problem, we obtain an update direction. We obtain an update direction delta x, which we then use to update the solution x1, x2. Okay, and we go for step 5. So step 5 is to update and repeat as usual for most numerical processes. So the process is repeated iteratively until convergence, where the change in the objective function and the constraints is small enough. Okay, that may take a whole lot of iterations. Okay, so at this point, let's go and see the Python code so that because having to do this manually is going to be a lot. All right, so what we have here. we define the function. This is x naught x1 squared plus x2 squared. Or we just this is like x1 squared s2 squared. Define the function we are trying to uh minimize or so. And then we have the equality constraint, which is x naught plus x1 minus 1 equals 0. And then we have that, x1 plus x2 equals 1. So it's better we transfer it to the other. So we can have it as a function like f of g of x, right? And then we have the inequality constraint, which is x1 minus 1 less than or equal to 0. So we have that to be x naught minus 1, if you like that. So then we have the Hessian. So the Hessian of the objective function, since it is quadratic, that is where we got our 2002 from. That's exactly this. So that's we do the second derivative of that expression. Then now we have the initial guess, and x naught is 0 0.5, 0 0.5. And then, of course, we have all of these other things. And you can study this. You can find it on Facebook. I'll put it right there. So you can copy that and try to play with that. So here you have how many iterations? One, two. So the first iteration we took 0 0.5, 0 0.5, which will give us 0 0.5. And then the search continues. So this goes to 0 0.6 and this is 0.73. So you see this one is increasing while this one is decreasing. In fact, okay, this one goes to 1 and then so 0.76, 1.00, blah blah, and so on. So you see the values are getting close, and here this is going until it gets into negative. And at the end of the day, the optimization is successful after 1, 2, 3, 4, 5, 6, 7 iterations, and the optimal solution ends up being 1.00. And in fact, that's roughly 1 and 0 in short. That's roughly 1 and 0 if you look at it. And then we now have objective function value to be 1.00. That's basically 1 in short, because you have x1 squared plus x2 squared. So if you put this is the x1 is 1, x2 is 0. So if you put 1, the answer ends up being 1 like this. So that makes a lot of sense. But definitely the SQP is meant for problems tougher than this one. But we just use this as a good example, for what it can do. So we see that using SQP in this situation, right? Uh, okay, from what we can see from the code, using SQP for f of x, I mean, for f of x comma y, we have we have x1 star to be approximately 1 and x2 star is approximately 0, and f of x1 star, x2 star is approximately 1. Okay, so with that in place, we can then let's talk about some other aspects. Say, let me change to this and say this. Yeah. So what are some advantages? Advantages of SQP. So, I mean, most of the times when we do numerical analysis, we are not solving the ideal problem. So, we are just solving a problem to give an example. So, it may look like it's a waste of time while we're doing this, because we could easily use Lagrangian multiplier to solve that same problem without stress, and we get probably a better answer. But SQP takes care of methods that are more difficult than that. So, of problems more difficult than that, I mean. So, SQP methods are highly accurate for smooth for smooth differentiable optimization, for smooth differentiable optimization problems with nonlinear constraints. In fact, the constraints we have in this case, I think it's even linear. So, but it's basically better for nonlinear constraints. If you look at the constraints we have here, they are both linear. Looking at the problem, so this is linear, this is linear. Okay. So, but I mean, just to demonstrate how this works, actually. So then the other thing is that they converge quickly. They converge quickly when when the initial guess is close to the solution. Okay. And then we have the disadvantages, right? Disadvantages, disadvantages of sequential quadratic programming. So here, the computational cost, you can see the process is a lot. So the computational costs can be high, especially, 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 especially in high dimensional problems due to the need to solve a quadratic sub problem at each iteration. Okay, then the method requires the the computation of second derivatives. I think we came about something like this under Newton's method. The computation of second derivatives, which is the Hessian. That is where we got the matrix from. Matrix 2002. That's the Hessian, which may be computationally, expensive for large problems. I mean, that Hessian pattern, I'm not sure it is well articulated when we talk about the solving quadratic subproblem. I'm not sure it is well articulated under the methodology. I think this is where it should have come up. This is where it should have come up. So I think this delta f of x, delta x, I think this is where the Hessian should have come up, because after this now, when we go to the quadratic subproblem, this is like half delta x. Then this is like the Hessian matrix of f of x. Now, this is it right here. It wasn't well articulated up there, but I mean, we can follow it up from the problem. Yeah. Yeah, we can follow it up from that problem right there. And oh, yeah, this is it. This is the Hessian. Yeah. This HK. Yeah, I think it's fine. HK, that's the Hessian, except that, in what we did there, so that it was coming first. So I think we're good. Yeah. So this in the articulation, this is what we have, and this came second. So this is the H sub X, which is the Hessian. Yeah. So that makes plenty sense. Okay, so with that done, you see that the SQP, see that SQP remains a powerful tool, a powerful tool for solving nonlinear optimization problems, nonlinear optimization problems where constraints play significant roles, okay? So, I mean, it's one way to deal with, I think Lagrangian can only deal with equality problems. So that's why SQP may be necessary, okay? So I think once we have mixed constraints, we may need to resort to this method. Thankfully, we can go the way of coding if the problem is too complicated. That's the interesting side of it. So, before I call it a date, can we take a look at some practice question, maybe one or two practice questions? Okay. Because maybe I'll just say this once without writing. Explain the key idea behind sequential quadratic programming and how it differs from other optimization methods. What is the role of the Lagrangian function in SQP? Why is a quadratic approximation used in SQP instead of directly solving the nonlinear optimization problem? So I think that's probably because of the nature of the inequalities or something like that. What conditions determine the convergence of the SQP method? How does SQP handle inequality constraint differently from equality constraints? That said, let's take one or two problems. Okay, let's take the first one. Given the optimization, given the optimization problem, which is to minimize x1, x2, where we have x1 minus 2, x1 minus x1 minus 1 squared plus x2 minus 2 squared, subject to x1 plus 2x2 minus 3 equals 0. So here we have only one equality constraint. So compute the gradients, of the objective function and constraints. Okay. The next thing, set up the quadratic subproblem. Set up the quadratic subproblem for the first iteration. Okay, that's question 1. So for question 2, let's go this way. Okay, I think I want to stop with this one question. This other question is something we've just taken care of. Yeah, let's just leave it as one question. Yeah, let's leave it as one question. Right, so that's what we have for sequential quadratic programming. Okay. Yeah, so let me see your answer in the comment section, either on Facebook or on YouTube. Then, of course, you can catch the code on Facebook, not on YouTube actually, because somehow I can't do that because of some special characters on the code. And then, of course, let me know in the comment section how helpful these videos are. Let me know if there's a problem you'd like me to solve or a topic you'd like me to teach. Also, if you have subscribed, thank you very much. If you have not, please go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.